a problem for me. Joonkyung, is that the right? How would you pronounce it? How do you pronounce it?
Joonkyung.
Yeah.
Yeah.
Okay, and he will talk about some graph norms.
Thank you very much for the introduction, and yeah, it's my great pleasure to be here. And I would especially thank the organizers for this great workshop, which I've been waiting for the last 2 years. Yeah, so I'm going to talk about some recent developments on graph norms. So as you all know, in the theory of dense graph limits, I mean, it's the theory of limits. So there should be some metric or norm on the space. So, and as you all know, this cut norm especially provides the cut metric, which is a standard metric in the theory of dense graph limits. So, and another key parameter in the theory of dense graph limits is, again, the homomorphism density, which I denote by th, t sub h. And yeah, this is one of the key theorems in the theory, which says that the sequence of graphs is convergent if and only if the h count converges for every h. Right, and having seen the importance of these h counts, it is kind of natural, at least for me, to ask, can a single h count give a norm that may replace this cut norm? I mean, if we can, having seen the importance, it's, for me, it's natural to wonder if such a replacement is possible on the vector space of symmetric functions. And yeah, so this was actually answered at least partially in 80s. So the famous Chong-Graham-Wilson theorem.
Quick question, your functions are not bounded, right?
I mean, it's, let's say bounded. Yeah, let's say bounded. Yeah, it's possible to like extend it to like LP, but yeah, for safety, let's say it's bounded. Yeah. Okay. Yeah, so this was the Chong-Graham-Wilson theorem, which is phrased slightly differently in terms of this language. So the Chong-Graham-Wilson theorem basically says that we can replace this cut norm by using the even cycle counts. And yeah, these are the even cycles. And yeah, this is a cornerstone in combinatorics. And yeah, one may ask why. Why is it so special about the even cycle? What's so special about the even cycles? Well, here's some reasons, some quick reasons, because they correspond to these norms in the spectrum. So if you consider this symmetric matrix and you look at the spectrum, and yeah, and that just corresponds to the L2K norm of the spectrum, which we often call Schatten norms or Schatten von Neumann norms. Yeah, so this is a very brief reason. And yeah, as I said, this phasic fact is a cornerstone in the theory of quasi-randomness. And this also inspired lots of work by Gowers' proof of Semiradis theorem, for example, the Gowers norms. Right, so.
The previous one, the K is fixed. What is 2K?
2K is the length of the even cycles. Yeah.
You need all even cycles?
No, just single even cycle does.
I don't understand this at all. So you're saying if I have the subgraph density of one of them, I'm done in identifying the graph?
No.
Sorry,
That's why
I'm missing something.
So what I'm saying is you can basically. So what you want to say is you compare two graph ones, say, by using the cut norm, and this can be completely replaced by using, say, 6 cycle count.
Okay, to identify them. Okay.
Yeah.
Okay.
not give you the distance between. Right? It won't give you the distance between.
Distance between, I mean, these two norms are topologically equivalent. Yeah. Yeah, and the quantitative equivalence is polynomial. Yeah.
So sorry, you're not comparing the six, as he was asking, you're not comparing the 6-cycle counts of two graphs. You're computing this quantity for the difference of these two graphons and minimizing overall rotations and so on.
So I'm talking about norms rather than the distance, the cut distance. So let's just skip it to the side. What I'm saying is, as I say, yeah, just replacing this cut norm by the six cycle counts normalized.
Just don't say, I mean, just leave this parameter.
Yes, let's leave the permutation. Yeah.
Do you still take the absolute value inside this integral or not?
That's a great question. So you can leave it like this, or you can take the absolute value here or inside, or you can you can leave out the absolute values because your 6-cycle count, as you can see, it's always a non-negative number. Yeah, that's some 2k power of some reals. So that's always non-negative number. So yeah, either is fine.
So could you just clarify? So you're saying if two graphons, general graphons have the same density of 6 cycles, this implies they're the same?
No.
Okay.
I'm confused about the difference.
You want it for all number of 6 cycles for weighted graphs.
Okay.
And then if the difference of the two graphs has.
Yeah. I see. Okay, great. Thanks.
Can you explain?
So having the same 6-cycle count doesn't necessarily mean that the graphons are the same.
Very good. So what are you doing?
So here I subjected to. Yes, here I subjected to. So it's different from comparing the 6-cycle counting here and 6-cycle counting here.
6. It's like it's like that is
There should be some multilinear extensions.
I don't understand. The thing that you bounded above by is only looking at the 6 cycles.
Yes.
So if that goes to 0, then the
Maybe not linear. Essentially, it's a number of 6 cycles of W minus W prime is 0, then W equals W prime.
Yes. Yeah, that is true.
So weighted number of 6 cycles.
If two
It's
graphs,
the total weight of the
put on
sign.
the edges
6
minus
cycles.
sign, depending plus sign or minus sign, whether one of them has an edge or the other, and calculate the 6-cycle counts by weighting cycles by the minus signs.
Is there anything special about 6, or will it work for large?
It works for all even cycles.
All even.
Yeah. As I say, this itself is a norm and the spectrum, and hence it also defines the norm in the original space. Yes, which we call Shetland norms. Okay, can I move on?
confusion is resolved.
Yeah.
I think you're still confusing people. So.
Yeah. So the question is, what's so special about even cycles? Can you use different graphs to do the same thing like this? I just replace this 6-cycle by some general H. So this is the question, but to formalize this question, let me just be precise as much as possible. Just
You know
not
what?
to confuse
Do us a favor. Why don't you write out, let's say, the 4-cycle in terms of an integral so that we see explicitly what you're doing there.
Okay. Yeah.
And I think that may help people with the confusion.
Can you use a marker then? Marks, yes.
And use a new marker.
Blue? Yeah, this seems to work.
So, and W is just some function, okay?
Yeah.
And if you think of W as an operator, then this is the trace of W to the power 4. Okay, and if the trace of W to the power 4 is 0, then W must be 0 as an operator. And if it's 0 as an operator, then W must be 0.
Yeah, thanks for the help. Yeah, so here's a question, and yeah, let me just elaborate. So on the vector space of the symmetric functions, the symmetric real functions on a unit square, we want to find H such that either this, which we take the absolute value outside of the H count, and or we can take the absolute value inside the H count, just like we do for these usual LP norms. We can just replace each of these W's in terms of their absolute values. Yeah, so there are two different concepts that we can take. And the latter one, being a norm, is a weaker property. So from now on, what I'm going to say is, if this defines a norm, then H is norming. And if the latter one defines a norm, then I'm going to say H is weakly norming, because the latter one is a weaker property. Okay, so here's Latzi, who asked the question. So he asked what graphs are norming, and later on, yeah, when Hatami studied what graphs are norming, he also asked what graphs are weakly norming. And I would say this is a beautiful question where combinatorics, linear algebra, function analysis, I mean, you already seen quite a bit, right? And probability and even group theory met. So yeah, yeah, the purpose of my talk is partially to like convince you that this is a beautiful question where lots of areas meet. Okay, so
sorry, are bipartite graphs a good candidate?
Yeah.
So he's asking whether bipartite graphs are a good candidate.
Yes.
Do we have anybody online, or is this an exercise in futility? Okay, I think if people are online, they could speak up and we can hear them. So is anybody online?
I'm online. I'm waving.
Good, thank you. So it's not a futile exercise. We do it for you.
Yes, you do it for me, and I'm listening, and I'm very appreciative. And I like your comments, Christian. You've been making very interesting comments all the way through.
Someone has eyes to say hi. Okay. Can I proceed? Yeah, so one of the motivations why we study this question is the famous conjecture of Sidorenko, which is also conjectured by Erdős and Simonovitz in a slightly different form. Yeah, it states the following: let H be any bipartite graph, then this inequality holds for any graph on W. Right. So what does it mean? That means the H count is minimized by the random graph, basically asymptotically minimized by the random graph GNP with the same density. If we fix the density, and if we want to minimize the number of bipartite graphs, then the choice must be the random graph. So let's say if this inequality holds for all graph on W, then H is Sidorenko. There are lots of Sidorenko graphs are known, including my results with various colleagues. Well, but it remains open. And the smallest open case so far is this one, the K5 phi minus C10, which we call the Möbius strip. And this was actually one of the examples suggested by Sidorenko himself in this 1992 paper. But still, no one ever managed to either prove or disprove that this graph is Sidorenko or not. So it's a very frustrating, infamous example. And here's an application of the weakly norming property. So every weakly norming graph is Sidorenko. And in fact, a much stronger correlation inequality than this Sidorenko property holds. So this is an observation by Balázs Szegedy, recorded in Hatami's paper, saying if H is weakly norming, then for every subgraph F, you have this inequality. In particular, if you take your F as a single edge, then you have the Sidorenko's property. So, and there are other graphs than weakly norming graphs that satisfies this very strong correlation inequality, which we call dominating graphs. Yeah, so I included this result just to motivate myself and probably David to write it up quickly. Yeah, so yeah, for example, you can prove the same inequality for every even length path, which has been known since I think 90s or 80s, yeah, by the work of Erdős and Szymanowicz. Okay, so this is one motivation, and let's have a look at some sufficient conditions for these weakly norming or norming properties. Right, so here are some results known. So Hatami in this 2010 paper proved that hypercubes are weakly norming, and the complete bipartite graphs with m vertices and n vertices on each side are also weakly norming, and if both are even, then it's norming. Yeah, this is what Hatami proved, and he also rediscovered this result by Chonger and Wilson about even cycles in terms of this language. And then Lazzi proved in his book, so there is a chapter 14, which covers pretty much about this stuff, that he where he proved that KTT minus a perfect matching. So this is one example. So I took K55 and then removed one perfect matching. Okay, so these are weakly norming. And this was generalized by myself with David, saying that any reflection graphs, which I'm going to define in a few minutes, every reflection graph is weakly norming, and there's a stronger notion that we call stable reflection graphs, which are norming. So this, for example, includes all these known examples so far, and I add many more. For example, the one subdivision of octahedron or the one subdivision of complete graphs. Yeah, these are all examples. These are two examples, and it also includes all the incidence graphs of regular polytopes. You can also replace a regular polytopes by a simplex, saying if you build a bipartite graph with k sets on one side and the r sets on the other side, and you draw an edge if the R set contains a K set. Yeah, if you consider such a bipartite graph, which we call set inclusion graph, then it's also an example. And here are some necessary conditions. So yeah, as you asked, these weakly norming graphs are necessarily bipartite because it's a bit of overkill, but it's necessarily Sidorenko, and Sidorenko graphs are necessarily bipartite. And moreover, well, let me just recall that this fact that every weakly norming graph is Sidorenko. And Hatami also showed that it must be biregular, which means it's a bipartite graph, so you have two parts. And at each side, you see the same degree for every vertex. So it's biregular. And myself with Frederick Garbe and Jan Hladky proved if it's disconnected, then all its components must be isomorphic. So it's a very symmetric graph. And one good thing here is that by using this theorem, we can always assume that our weakly norming graph is connected. And later on, Sidorenko proved that it must be edge transitive. So it's a very symmetric class of graph, which we can describe like this. So every bipartite edge transitive graph is a G1, G2, G graph, say. So what do I mean by G1, G2, G graph? It's a graph constructed by a group G with two subgroups, G1 and G2. So on one side, you just collect all these left cosets of G1. And on the other side, you just collect left cosets of G2. And you put an edge if they intersect. Okay. Actually, this encodes all the bipartite edge transitive graphs in terms of like group theoretic language. And so here's a definition of the reflection graph. So reflection graph, due to myself and David, is a G1, G2, G graph with very particular choice of groups. So here, G must be the finite finite real reflection group, not even complex. And G1 and G2 are parabolic subgroups. So what do I mean by parabolic subgroups? So we have a complete.
What is a reflection group?
So yeah, reflection group is a group generated by hyperplanes. It's a finite group. So due to the classical work of Coxeter, we have a complete list of finite reflection groups. Yeah, and the parabolic subgroups are generated by the standard generators, which we call simple reflections. You can just think of some hyperplanes, some standard hyperplanes that generates this group.
Can you be, I mean, maybe I'm the only one who is not a group theorist, but otherwise, could you draw some pictures? And are your hyperplanes in RD or the hyperplanes some abstract hyperplane? What do you mean by?
Yeah,
so, and how do you generate a group from it and so on?
Yeah, so one example would be you take the simplex, say something like this, and you can think of the symmetries of the simplex, which means you can consider the hyperplanes which cut this simplex into the same half. So this is one hyperplane we can consider. And there are other hyperplanes like this, or some other hyperplanes like these. Yeah, and so on. And
it's the reflections about the hyperplane generators for you.
Yes. Yeah. And if I collect the hyperplanes that have that form this chamber, I would say, so that makes this triangle, then these are simple reflections. So these three hyperplanes that that surrounds this triangular region, they generate the whole group, and these are the standard generators of the symmetric group, which corresponds to transpositions. Yeah, and if I take a subset of these simple reflections and generate the subgroup out of it, then it's so-called the parabolic subgroups. Okay, so yeah, these are some necessary conditions. And well, the bad news here, or good news, is none of these necessary conditions are sufficient. So due to the result by Crow, Martin, Spock, and Rockna, yeah, there exists a edge-transitive Sidorenko graph that is not Wickman-Norman. So even if we assume all of these edge-transitive Sidorenko biregular, I mean, edge-transitive graphs are necessarily biregular, but even if we assume all of these, it can be not Wickman-Norman. So here's the situation. So we have reflection graphs due to the result of myself with David. It's necessarily, these are Wickman-Norman graphs, and Wickman-Norman graphs are necessarily edge transitive, but the inclusion here is strict. Okay. And here's the ultimate goal, which is a conjecture of David, saying that the examples we found here should be.
How should the proof goes of this theorem? Like
here from here to here.
Yeah, like
We want to know how the proof goes.
Oh, okay.
There exists an extransitive Sidorenko graph that is not
this proof. So there's, yeah, you will see some equivalent conditions, and one of the equivalent conditions is but using convexity, basically. Yeah. So it's so-called the step Sidorenko property, which is substantially stronger than the Sidorenko property. Yeah, and then Dan and colleagues use this property to like basically refuted convexity. Yeah, so that's one way. Yeah, so I mean, to prove this is a great conjecture.
Sorry to interrupt. I was wondering, is there anything special about the left coset? Can you switch to?
No, you can use
What about
right
like
cosets.
one left coset, one right coset?
That would be a different story. I've never thought about it actually. Yeah, but I mean, you can choose left or right. but one left and one right is a different story. It would give a different graph. So yeah, I think that's not possible. Yeah, I suspect. Yeah, so yeah, so to prove this, I mean, one side is already there. So if reflection graph, then weakly norming, or if stable reflection graph, then it's norming. So we need to prove the converse. So to just illustrate where we are, so we do know that a weakly norming graph is edge transitive, which means it's a G1, G2, G graph I described. But the task is now to nail down these G to be the one of these list of finite reflection groups, and G1 and G2 also should be these very special probabilic subgroups. So, but what's hard is, I mean, we are basically dealing with some average. So this H count here is some average, and this doesn't really contain any kind of algebraic information about the automorphism group of H. I mean, it does contain something, but it doesn't contain many kind of detailed information about the automorphism group. Yeah, so this is the hardest part. And this is the ultimate goal. Okay, so let me just describe this property more properly by introducing some equivalent conditions. Yeah, so recall that this is my H count. So I take this bunch of product of the function W, and I just average, or I just take the integration. And the following are equivalent. So the first property is the definition, H is weakly norming. And the second one says this is a convex parameter on this convex set. So it's a positive orthant basically. So you're looking at those functions with non-negative values or positive values, and that defines a convex parameter in this positive orthant of functions. And the third one is we can actually drop off the symmetry assumption. So because it's a bipartite graph, without the symmetry assumption, we can naturally define this function over here by giving a direction from A to B. Okay, and then we can just do the same thing for these bigraphons or asymmetric graphons, and then it's actually equivalent. So this H defining a norm in this larger space is actually equivalent to the weakly norming property, which we originally had for the symmetric functions. Okay, this is one example of equivalence. And let me just describe how one can use this to attack some problems. So this also connects to what Dan did with his colleagues, basically using refuting convexity. Okay. So this is my result with Bjarne Schurke, who's now at Caltech. So here's an example. So let's consider G as an n by n symmetric matrix or a block graphon. Then it forms a homogeneous polynomial of degree being the number of edges in H. So here's an example. So this is a two-edge path. And if I count this two-edge path in this block graphon or a 2x2 matrix, then it corresponds to this quadratic polynomial. And this quadratic polynomial we can represent as a sum of squares, just like this. And yeah, this sum of squares gives the convexity. So we can say that H is weakly norming, yeah, by using this. But there are some graphs that give non-convex polynomials. For example, the K5 by minus C10. This guy gives a non-convex polynomial at around some point that we've found. or even a generalization, any kind of twisted odd cycles of full cycles. Yeah, these give a non-convex polynomials. So as a corollary, we did manage to prove this notorious example is not weak norming, which was a question by Hatami. Okay, so this is one example application. And for norming graphs, which is a stronger property, we have more interesting number of equivalents. So the first one is the definition, H is norming. And Lovász's observation in the book says that we can actually drop off the absolute value because your weighted H count would be always non-negative. So this is Lovász's observation. And our theorem, the theorem of myself with Bjarne says it is a strictly convex parameter on the whole vector space rather than the positive orthant. And the fourth one is, well, we can actually, again, we can drop off the symmetry assumption to move on to the larger space of the asymmetric graphons or bigraphons. And the last one is particularly interesting, I would say. So this says it defines a norm on the vector space of complex valued functions. But here, the last one is a little bit incorrect because for complex norming, let's say, we need some two-edge coloring of our H to assign these conjugates to the values. Yeah, so this was already, this has been used by Gowers for his definition of octahedral norms or Gowers norms in this context of additive combinatorics. And it's actually very natural to consider these complex valued functions because, especially in the context of the additive combinatorics, because if you take the Fourier transform, then it gives you a complex valued function. And and if you consider the inverse transform from there, then it will also give you a complex valued function, right? Right, so this is my precise statement with Sasha Sidorenko, saying that a graph is complex norming if and only if it is norming, which means there exists a two-edge coloring that allows us to define a norm for this larger space of complex valued functions. So so this is the precise formula that we can take. Looks a little scary, but I mean, this alpha is just some 0, 1 valued function for each edge. And if I take alpha to be 1, then I take non-conjugate. And if alpha is 0, then I take the conjugate. So this is the formula. Yeah, and here's an example, again, for a full cycle. So if I color my full cycle in such a alternating way, then this corresponds to this average with complex valued functions. And that also corresponds to the Schatten norm or the four norm of the spectrum in the complex setting. Okay, so why is this interesting? Because we can actually use this theorem to prove something about norming graphs. So we can actually prove that this alpha must be unique up to isomorphism. And moreover, it's very, very symmetric. So we can extract some combinatorial properties of alpha to use it, to apply it to different problems, to distinguish these norming graphs and weak norming graphs and prove something is not norming, something like that. So one theorem of ours says that there uniquely exists a transitive two-edge coloring, which means there is a color preserving automorphism on my graph H, and there's also a color reversing automorphism on H. So by using this fact, we can prove various things. And moreover, this alpha colors each shortest cycle in either monochromatic way or like half way, which means I'm using the red color for the half the edges and the blue color for the rest of the edges. And it must also maximize the number of alternating shortest cycles. For example, if you look at this example, so this is precisely the 2H coloring that makes the one subdivision of octahedral norming. And you can actually see that all these 6 cycles, which are shortest cycles, are colored in an alternating way. So red, blue, red, blue, red, blue. Yeah, so this must be the case for every such coloring. Okay, so here's one example application. So let me just prove this fact. So if H is norming, then there exists a balanced 2H coloring, which means every vertex sees the same number of red, blue colors. Okay. Yeah, so what I can do is to take this complex valued function. So by using this complex valued function, what I can do is, well, if I count my H in this particular alpha coloring, then then what I get is just this formula where my D1 and D0 denotes the color, the number of colors that my vertex V sees. Okay, and yeah, it's a standard fact that if this D1 minus D0 is non-zero, then this integral is 0. So what it says is if this is non-zero, then we have both the H count in F conjugate and F are 0, and hence we have a non-zero real valued function which gives 0 for this H count. But if you think about the definition of norms, this is not allowed. So which contradicts the real norming property of H. So this is one example application where you can say, well, there's a kind of symmetric balanced 2H coloring of H. Yeah, so this is one example application, and we apply this result to prove various necessary conditions for the norming property. For example, we can actually prove that this G1, G2, G graph, I mean, every norming graph is weak norming and hence H transitive, and hence it's a G1, G2, G graph. So the game is what we can say about these groups. So for example, we can say that G has an index 2 subgroup. So which is non-trivial. I mean, of course, not every group has a index 2 subgroup. And if you take a finite reflection group, then there's a very natural way to take a index 2 subgroup. For example, in the alternating group, you can just take your, in the symmetric group, you can just take the alternating subgroup, which is index 2. And this just generalizes to all the finite reflection groups. Namely, you can just take those words that have even length. Yeah, then that forms a index 2 subgroup. So this corollary can be seen as an evidence for this grand classification conjecture. And our method also answered the last outstanding question of Hatami. So Hatami actually left like 6 questions, and many of them answered by like Dan and colleagues and myself and so on. And the last outstanding question was whether these D-dimensional hypercube, which were proven by Hatami to be weakly norming, are norming or not. And we answered this question. So whenever D is greater than 2, this is not norming. And when these 2, this is just 4 cycle, which is a typical example of norming graph. So yeah, we are done with hypercubes. And there are other applications of the result saying we try to classify the bipartite Kneser graphs, which means we, on one hand, we collect the R subsets of some N set, and on the other side, we collect its complement, and we put an edge if they are disjoint. So this is a bipartite version of Kneser graph, and we actually classified all the Kneser graphs. And one subdivision of KT is another example. And more generally, we try to classify all these set incidence graphs I and KR, which means we collect the K set over R subsets from my N set, and then make the set incidence graph, set incidence bipartite graph out of them. Well, we are quite close, but the list is not complete yet for the set inclusion graphs. So yeah, there are lots of examples, example applications by using this complex norming property. Okay, so let me, how much time do I have? Yeah. Okay, yeah, so let me just wrap up by introducing some open problems. So one question is, can we classify all the norming reflection graphs? So reflection graphs are known to be weakly norming, but distinguishing between these weakly norming and norming property is an interesting question. And the more applications of the weakly norming property, especially the correlation inequality I showed. Yeah, this inequality has been useful in various different contexts, especially in the theory of quasi-randomness, or the common graphs, or even other extremal graph theoretic questions like supersaturations, or even the extremal number or Turan number itself for the bipartite graphs. Yeah, it has been applied in various different contexts, so I would love to see more. And another question is there a stable cut involution in a weak norming graph, which means, so in a reflection graph, the geometric reflection themselves corresponds to a very natural involution on the graph. For example, you can see these blue parts and red part in this 6 cycle corresponds to each other by, say, this reflection along this along this cut. And there are other examples of such involutions for reflection graphs. So if the grand conjecture, the grand classification conjecture is true, then this must be true. But no one ever so far managed to prove that there exists one such involution, which can be seen as an evidence of the existence of the reflection in the graph. And this also connects to the positive graph conjecture, which states that if I consider this H count in the weight setting, and if it's non-negative for any possibly negative W, then it implies there exists some kind of mirror type symmetry in this graph H, so which we call the stable involution. For example, you can see one example in this 6 cycle where if you want to count the 6 cycle in the weighted setting, what you can do is basically fix your 2 vertices and take the average, the weighted average of the path of length 2, and just square it. So because of this square structure, no matter how you choose your weighted graph W, the 6 cycle count must be non-negative. And the positive graph conjecture states that the converse must be also true, which means if we have non-negative H count for every weighted W, then your H must have such an involution therein.
The cut has to be independent.
Yeah, it must be an independent set. Yeah, so this in particular is not a stable involution. Yeah, and this positive graph conjecture is a beautiful problem. And in the paper in the paper where this conjecture appeared, this case of norming graph was mentioned as a particular interesting case. And if there exists a stable involution in norming graph, then it basically proves the positive graph conjecture for norming graphs. Yep, so this is it. Thanks for listening.
Okay, so yeah, very nice talk. I guess just 2 small questions. So I guess in probability, there's like this moment question, which is like, what if I give you a sequence of numbers, does it uniquely determine and I tell you it's the moments of a distribution, does that tell you that, does it uniquely determine the distribution? So I guess this is called the hamburger moment problem. And so I think this is sort of remarkable. You're saying that in this space of graphons, if you have like finitely many moments in some sense, it sort of uniquely determines graphons. But so I have 2 questions. So one is, what is this? Why should a non-expert care about this weakly norming versus norming? Like, what's the importance of this problem?
So the way I see is whether you can define some H count in a global sense. You can define a convex parameter globally on the space of on the vector space, or you just restrict yourself onto the positive orthant or the convex set of graphons. So so the way I see this problem is a challenge to convexity that we've been using. And yeah, these lots of convexity inequalities in this graph limits context has been very useful in attacking, say, Sidorenko's conjecture, or even this like lower tail problem in this dense random graph setting.
Mm-hmm.
So it or the proof of Semradi's regularity lemma. Yeah, so it's been useful for various contexts. So I think it's in general very important to understand the strongest possible convexity inequality in such a way. And this question really connects to such a philosophy.
Okay, thank you. And the second question is, so there were some of these results which seem to say, if you want to prove something for like graphs, so sort of symmetric graphs, somehow if you prove equivalent things for bipartite graphs,
yes,
then they're kind of equivalent. Is there any intuition like why you can move between like normal symmetric graphs and sort of bipartite graphs?
Yeah, I mean, we were kind of surprised. Yeah, so the thing was the known technique before the theorem worked both in this asymmetric setting and the symmetric setting. So we kind of suspected that they might be equivalent. But it just worked. And as an application, it also simplified some of the known results. For example, the Hatami's biregularity theorem. If you pass to the bigraphon setting, it's just 2 lines. So I would say just heuristic like experience from like applying these techniques to different settings.
Thanks.
So this may follow from many of the results that you stated, but apart from the cycles, are the complete bipartite graphs, are they norming? The strongest one, are they norming?
So if you assume both sides are of even size,
right?
Yeah, then they are norming. Yeah. So there's some parity issue there, because in norming graphs are necessarily Eulerian, which means every vertex must have even degree.
I see.
Yeah. So yeah, complete bipartite graphs must be
And thank you. And there seems to be a lot of references. Is there a good monograph, or is there a starting point?
So for that, I would say my paper with Sidorenko is the most recent one. So it should include like as many references possible so far. Yeah.
Sure. Thank you.
It seems to me that norming is much more stronger than weakly norming. Is it possible that actually for norming, the characterization is true, that it comes from stable reflection groups, while for weakly norming, it is not true? I mean, so it might occur that one of the conjectures is true and the other is not.
I don't know, but I believe this classification conjecture is true. Yeah, so that's my belief. I mean, when I wrote this paper with David, we were not brave enough to conjecture that the examples we found are just all of them. But after years and years, we tried many things and we found new necessary conditions, and it kind of suggests that the conjecture could be true. I believe so.
More questions? Okay, thank you again, and let's have coffee.